Welcome back. So what is our, what's on the agenda that needs to be done by tomorrow night? The test, okay. So I noticed a number of you have done it, and that's good, and I'll talk a little bit more about that. Just make sure you have taken it by tomorrow, I think at 11:59 at the latest, but it started early enough so you have time. Don't try to start it at 11:40 and try to get it all done. And if you get it done tonight, that'd be great. So what should we go with the word of the day for attendance purposes? Test. Seems fitting. Sort of what I was thinking too. So just a reminder, test is due. And that'll be our word of the day. Tonight we're going to look at 11.5 and 11.6. So we're going to look at how to take the derivative of an exponential function, how to take the derivative of a logarithmic function, and these are ones that are kind of different than what we've done before. They have the chain rule and possibly the product rule embedded when we need to take them, so that's why I guess they decided to do those last week. And then the last section, there's only actually 5 questions for 11.6. It's called implicit differentiation. I'm going to show you sort of how I've learned to do it rather than trying to go through how the book works you through it. It's kind of confusing, but it's actually very simple if you just think of it. So I'm going to show you the simple way that I learned to finally think about it after going through years of therapy and doing a lot of stuff, and said that stuff from the book just didn't make sense, and it was overly complicated. And so anyway, we'll make it nice and simple. Okay, so let me just save this. I'm going to show you, what am I going to show you here? Okay, so this is the beginning part. This is Canvas. And I'll just talk you through it in case, because I noticed I got a couple emails of people who are having difficulty getting the lockdown browser, and it's not as straightforward as I would have thought. But what you have to do is from within Canvas, you have to actually go ahead and try to take one of the quizzes. So like the unnamed quiz. It looks like we are streaming. So you go into one of the quizzes. You go to take it, but it won't let you take it because it says you need the Respondus Lockdown browser, so then you can download it from this link. I've already done that. It downloads, you install it on your computer, and then what you have to do is close everything else down, go into the Lockdown browser, and that will take you to re-log into Canvas, and then you'll be able to take the quizzes. Okay. I also got stuck here. I downloaded it and I came back in to try to take it, but you can't take it unless you close everything and then open the lockdown browser. So again, that's why it's good to test it out first. Okay, I'm going to leave student mode. Now, after you take the test, here's, last week we decided that if you can maintain a 90% average over the 3 tests we're taking, that you would earn an A in the class, assuming you did the homework too. If everything else was an A, if you got a 90% average or better, then you'll get an A in the class without having to take the final. Another option, or yeah, I guess it's an option. You'll notice now, after you take the quiz, right below it, it says something about for test corrections. I've got a sheet here, and it's both sides. Basically, some of the times you may have done the question, and there's a couple that are kind of close. One of the things you need to do is make sure you have like 4 or 5 or 6 decimal to accurately get the answer. If that was an issue, anyway, if you kind of understood what to do, or if you understood afterwards, what I'm going to ask you is you can do a test correction. What I will do is after Wednesday, so like Thursday, I will reopen up the quiz. Or how many of you have taken it? Are you able to go back and look at your answers? Okay, so that's available to you. So what you need to do is once you've taken it, if you missed anything, get one of these or something like it. It's just kind of a, there's a Word document available. You can pull that up. But what I'm going to ask you to do is write down the question number you missed, state the question, what it is, so I can see it, and then underneath, rework it for me, showing me your work, and that's your opportunity to explain to me that you kind of knew what you were doing, but maybe you chose the wrong one, or whatever you need to explain. But if you get the correct answer, I will give you half the points back at a minimum. And if you give me a really good explanation, I may give you more, up to full credit, if it seems like, hey, you probably should have gotten it right. But give me the better you do on your explanation, the more points you can earn. But at a minimum, if you get the right answer, you will get half the points back. So it turns an 80 to a 90 just by reworking them, getting the right ones. But if you give me a good story of why you, it's okay to say, hey, I blew it, I'm whatever it was, but I do understand it now, because I just want to see that, convince me that you understand it real clearly, and I can give you some more points, but a minimum of half. Okay, so I'm going to just kind of leave these up here, and before you leave, if you want to take some of these, that's great. If you want to just download this and type it up and then send it to me, that's fine. You could either turn it back into me at next class or the class next week or something, or you can take a picture of it and upload it to me somehow, send it to email, however you want to do it. But that's, because what I'm interested in is that you've learned, and a lot of times tests help you do that. Even though you missed it, you go back and look at it and say, oh, now I see. Or maybe you saw it at the time, but chose the wrong answer. Does that sound reasonable? Okay. And the 90% on average is after that's been added in. I don't keep track of what you had before. I only keep track of what you end up with. Okay. Very good. I'm going to look ahead. I think I'm looking at, I think there's one day where we only have one section. Is that correct? Has anyone looked at the syllabus recently? I think there's like we do a 14.1 or something. I'm looking at taking that last day and maybe using it to do a little bit more review. But so we may get rid of one of the sections, or I might leave it as extra credit. We'll see. Okay, so I'm looking at that because I've looked at other instructors' courses, and some have this section, some have that section. So I think there's a little bit. I'll look at what we have to have for the competencies, and what we don't need to have, maybe we can not have to worry about. Okay. Any questions? Okay. Good. So that kind of keep up. And there are no late penalties, so as long as you get things, the homework is all due, at least within WebAssign, has due dates to the 20th of July, so you won't get locked out. Canvas does have, I put in due dates, but those are soft due dates. You don't lose any points for going past them, but they are just there to kind of try to help you keep on track so you don't have a bunch at the end. Okay, so now let's go ahead and go down with that. Where's my notes? Okay, what kind of a function is this?
Log.
Bless you. What's that?
Log. Exponential.
Close. You got the.
Natural log.
Let's do over here. What kind of function is that? Natural log. So there's a lot, and they're related. A log function, logarithm, is the inverse of an exponential. Okay, so an exponential is repeated multiplication. So this is taking the base of e and multiplying it repeatedly x times. And does anyone know what the number e is? It's kind of a number like pi. It's called the natural number, and that's why the logarithm ln is the natural logarithm. I'll get you started. 2.72. Very good. Rounded, it's 718 something something, but we can usually use 72 approximately, so I should put some squiggles. So that's rounded to 2 decimal places. Okay. Actually, I'll go with 718 ... Okay, so it's a naturally occurring number. It's used quite a bit in finance. It's used in continuous processes, so that's why it comes about. Logarithms are the inverse of an exponential, so that's why we need logarithms, is to undo it. Just like when we multiply, what's the opposite of multiplication? Division. So with multiplication and division, we can do and undo things. With exponents and logarithms, we can do and undo things. Okay. I guess fortunately, we're not going to do a lot of algebra with these two because it can get a little complicated. We're going to do calculus with them. And the hardest part about these two is the derivative is so simple. And that, like the logarithm derivative, well, I'll do that one. There's really, I've never seen a good workout of why it is what it is, but if you take the derivative of g of x, does anyone know what we get? No. What's that? Close. 1 over x. So yeah, it's a very simple derivative. It's just 1 over x. When you take of the natural log, when you take its derivative, it's just 1 over x. And it feels like magic or it's something, but it is. It just is what it is. That's what it is. Okay. And even with the science-based calculus, there's not really a good proof of why it is what it is. Yes, sir.
Would this be related to the same as roots? You know how square root of x would be 1/2, or cube root of...
Possibly, yeah. I never really, I just accepted it and moved on. But I think you have something there, yeah, because the roots end up going underneath, right? You take a derivative.
Well, I thought the inverse of an exponent was the root.
You kind of, except that's for a set exponent. So like a square, the inverse would be a 1/2. So I think it is related that. That might be a good way of understanding. And when we take like a square root, when we take its derivative, it ends up in the denominator, right? Good. I'm 20 years, I never even thought of that. So that's cool, yeah. And the cool thing about exponentials is that when we take the derivative of an exponential, and let me just make this comment and see if you can figure out what the exponential is going to be. An exponential function, the rate of change of an exponential function is exponential. And the rate of change of a natural exponential, e to the x, is actually e to the x. So with that much said, what do you think the derivative of e to the x is?
X.
E to the x. Since, remember, the derivative is the slope or the rate of change of the function. And this one is, yeah, it's its own derivative. So its rate of change, it is its own rate of change, which is kind of weird. But that's maybe why they call it a natural number. It's the only function that does this, that is its own derivative. So if you take the derivative, you get e to the x. The derivative of e to the x is e to the x. it is its own derivative. Cool. Guess it's like cloning itself or something. And then the log function is an inverse, so but you can see quickly that if you take the derivative, the second derivative here, which we're not going to get into, this would be 1 over x squared of some sort, you know. So this is, if you want to think of it, you could write it as x to the minus 1. But the bottom line is this is what we're going to need to do. Now, that's if we have the natural logarithm and the natural exponential. But if we have anything else, so let's make another function. So where are we? Here we go. So EF, let's go with h of x. Let's say, here's another one, the doubling function, 2 to the x, right? That's going to double. If we want to take the derivative of h to the x, it's sort of like e to the x. It's also its own derivative, but there's sort of a correction. It's not completely its own derivative. Whenever we get this, we also get the natural log of 2, of whatever the base is. Okay? So if e is the only one, it's a very special case where it's really its own derivative. Every other exponential needs sort of like, I call it a corrective factor, which is just, it's its own derivative, but then it gets multiplied by the natural log of the base. Okay, just something you need to either remember or put in your notes. Okay, and you'll see this in the book. They'll, instead of using 2, they'll use the function, I'll just do it down here, b to the x, and this is kind of sloppy, but I'm going to take the derivative of b to the x, and I'll just say it's b to the x times the natural log of b, and b could be any number. Okay, so that's just kind of, you remember this and you do it. The thing we're going to see is that the exponents will be actual functions in themselves, and so we're going to see the chain rule will come out of this. But you always get, when you got e to the x, you always get it as its own derivative, and then if the exponent has a function in it, you take the derivative of the exponent as well. Okay. And over here, the same thing. Let's say E, F, G, H. I guess we'll do m of x. I don't know. So if we have a logarithm other than the natural log, so say the log, and I'll just use the general b of x. When we go to take this derivative, we get sort of the same thing. We get 1 over x. But then we're going to multiply by 1 over what? What's that? Good, close. But not just b. The natural log of b. Okay, and again, this is just something I wouldn't expect you to have known. The book doesn't really explain why it is, but it just says that's how it works. So yes, it'll be natural log of b. So a lot of times you'll see this just written as 1 over x natural log of b. I just think of it as a correcting factor because it's not the natural one, so we need to do this correction. Okay. Oops. So that's basically, I mean, with that, and you couple it with what we were doing with the chain rule and the product rule and stuff, you'll be able to do all of the problems in the homework. What I'm going to do is work through a few examples, and then, yeah, we'll just work a few examples, and then we're into explicit derivatives, which is actually going to seem easier once we're done with this. Okay. Any preference? Would you like to start with natural logs, or would you like to start with exponentials? Exponentials. Me too. The book starts with logs, but I would rather start with exponentials. So let's clear that out. So we're just going to take a look at a few examples together. Let's do an exponential. Shall we take a hard one or an easy one? An easy. Okay. This one. So go ahead and find the derivative of g of x. And I'll give you just a few minutes. We'll come back together, but give it a try. And this should be an easy one. Especially if you have the notes down on the last page. Can anyone help me with what is the derivative here? Yes, sir.
Is it 5 to the x times natural log 5?
Exactly. That's it. Oops, natural log of 5. That's the hard part for me, is they're so easy I mess them up because... And you could put the natural log of 5 in the front if you want, however, but yeah, it's just multiplied. So it's just its own derivative times this, I call it a, what did I call it? An adjusting factor. But I made that up, it's not in the book, so whatever you want to call it. It's going to have that natural log. Now let's do one that's a little bit more challenging. This one is going to be h of x. And this one we're going to do 3 to the x squared minus x. Now remember a chain rule from last week, from last Thursday. So I'll just walk you, we're going to take the derivative of the outside function, and then it's going to get multiplied by the derivative of the inside function. The inside function is the exponent. Okay. So does this one look startable, or would you like a little guidance through this one? Guidance would be nice. Okay. So the trick we do is we recognize that this is the inside function. And so one of the tricks we do is we just, let's make it simpler. Let's call that u. I don't know why they use u, but it seems like they always do it. They call it u substitution. And so in that case, what do we have? We've got 3u. So it's sort of a new function. If we took the derivative of 3u, what would it be? It would be 3u times natural log of 3. Okay. But this u, the reason we use it, and then the chain rule, we have to multiply by the derivative of u. Okay, so remember the chain rule, there's an outside function is the exponential. The inside, which is the exponent, has more complications. So if this is u up here, what's the derivative of u? 2x minus 1. Excellent. And so our derivative in the end is going to be, what is u? U is x squared minus x. So notice nothing changed. That's exactly what we started with. Times natural log of 3, because that's the natural log of the base, and then times the derivative of u, which is 2x minus 1. Okay. So part of these you might get to the place where you don't actually go do the u substitution. You might just look at this and say, where are we? You might look here and say, well, this is going to be the answer itself, right? Because with an exponential, we always start with the, just kind of go over here. The exponential itself is always part of the answer. Minus x. Okay, so we just rewrite what we had. We know that the base, when we take the derivative, if the base is not e, we do the natural log of the base, which is 3. And then we just take the derivative of the exponent, which is 2x minus 1. Okay, notice it's the same answer. So and sometimes that's less confusing than going to a u substitution and trying to work with all these parts. If you just kind of, but you have to be able to see it. It's always going to be the exponential itself, and that's what's kind of cool about exponentials, but it's also weird that it's its own derivative. Okay, so it's just rewrite the problem, and that's part of the derivative. Take the natural log of the base, that's part of the answer, and then just remember to take the derivative of the exponent, and that's really all you got to worry about with these. Okay, that's a lot of stuff, right? Simple for him to say, right? But yeah, these are a bit challenging. But the homework ones are not as bad. Okay, let me give you one with an e that'll make it a little bit easier, but of course, not too much. So I'm going to just give us some room here. Let's go ahead and do this one. Let's go for a moderate level of difficulty. So we're going to go f of x equals e to the 2x plus 1. So again, try it. Just rewrite it, because that's going to be part of its derivative. Natural log of e, and the natural log of e is always what? Anybody? 1. That's why we can, you don't have to write it, you could write it if you want. And then take the derivative of the exponent and multiply it. Okay, so that's the chain rule. Taking the derivative of the outside is itself times the derivative of the inside, which is the derivative of the exponent. That's the main thing you got to get used to here is with exponentials, the exponent is the inside of the function. One of the coolest things, you just rewrite it down, and that's part of the answer, right? It's part of the answer. It's its own derivative. And what do we, go ahead, 2. The derivative of this is x, bring down the 1, that's just 2. So we multiply by 2, because that's the derivative of the exponent. And you could put the 2 in front. Usually you would see it that way. It would be written as 2e to the 2x plus 1. Okay, so that's the derivative of the function itself times the derivative of the exponent. Why didn't we have a natural log of the base there? Why didn't we? Because it's e and the natural log of e is 1. So it is there, but it becomes 1, and 1 times anything, it just disappears. Okay, it's that algebraic disappearance. But I like to remember that it's there. It's really there with all of them. It's just when I have the natural log of e, it's 1. Good. It's just for consistency's sake. So far, so good. One more, just a little bit harder, but not too much. This should get you through the homework. Let's see which one. give that one a try. And I'll give you a little bit more time. Try it on your own. Remember, just rewrite it because it's its own derivative, and then multiply by the derivative of the exponent. The derivative of the exponent, typically you'll put it in a parentheses because it's the whole thing times that. How are we doing? What do we got for the inside here?
2x minus 1.
Excellent. 2x minus 1. Derivative of 1 is 0, so that's all there is. So it's its own derivative times the derivative of the exponent. Okay. And you could put it in front if you want, again, but that's pretty much what you're going to need to do. Okay, got one more for you, and then we'll move on to logarithms, and then so let me do it here because I think it'll help. So this one we're going to do, they call it S of x, and they give us x squared times e to the 2x minus 1. What are we going to need to use with this one from Thursday? The product rule. Okay. Remember, product rule is the derivative of the first times the second unchanged plus derivative of the second times the first unchanged. Okay. So we'll give it a try. We'll give it a step by step. There's the product rule. Take the derivative of the first one times the second unchanged plus the second one unchanged times the derivative of the second one. So can you see that the two parts are x squared and e to the 2x? Okay. So what's the derivative of x squared? Very good. The 2 comes down, becomes 2x, and then we just rewrite this function e to the 2x. We didn't do anything to it. Okay, just rewrite it. That's the product rule part. And then we get the second part where we take the first function, x squared, and we don't do anything to it except copy it down. Again, it's easy, but it's sometimes you're asking, why do I do this? It just works. It's a formula. Okay. And then now, what is the derivative of e to the 2x minus 1? That's going to go right here, right? There's going to be a 2 that comes down. But again, I always like to start, it's its own derivative, 2x minus 1, and the derivative of the exponent is 2. Right? 2x minus 1, the derivative is 2. So I'll do that. That's it. Now you could do some algebra on this, but I don't think you need to when you do the answers. Okay. I think a lot of them, they ask you just to not do too much algebra, not to simplify it. Just go ahead and write it like that. Okay. So again, yes, sir.
So the wouldn't it be e to the 2x minus? Would it be the same thing?
Yes. E to the 2x minus 1. And that's that part. But then we multiply it by the derivative. On this one, we'd multiply it by the derivative of the exponent. The exponent is 2x minus 1. And if you take the derivative of that, you get 2. So that's why I have to multiply it by 2.
That's not part of the s of x.
It is. E to the 2x minus 1. So this is like one function, and this is a function being multiplied together. So whenever you take the derivative of e to some power, and in this case e to the 2x minus 1, when you take that derivative, you're going to get itself times the derivative of the inside of the exponent. Okay, so it's e to the 2x minus 1. Well, let's just do that. So if I just had that, and I asked you to take its derivative, what would be the derivative? It's the same thing times the derivative of the exponent, because it's got a function up there in the exponent. Okay. So that's what this part here is, just up here. And notice it's times the original x squared, didn't get changed. We didn't take its derivative. How's that? Bringing back memories, fond memories or nightmares, one or the other. But a little bit of practice. I think the ones in the homework are not as bad. These ones are a little more challenging. Okay. So far, so good? Okay. Yes, sir.
For the test, are we allowed to use the study guide? I know you
Anything
said
you
we
want.
could use notes.
Yeah.
Is that okay?
1 page of notes. If you have a second page, I'm not going to, yeah. So yeah, a study guide is actually probably a pretty good thing to, if you go through it and have your notes on there.
That's, yeah, I won't have to work on the study guide.
Exactly. It's perfectly fine. In fact, because the problems are very similar. So it's good. And that's what I try to do, is if you can, I try to make the study guide like a pre-test, a different version of it. So if you've gone through that, you should find that the test questions are very similar. So it's just, I try to make the test just a verification that you did enough studying to know how to do it. And if I change the functions, you can follow along. And again, and not making the functions any more complicated. Okay. So let's do a couple of natural logs. And then we'll kind of be done with this section.
What about normal logs? Like log 9 stuff?
Well, let's start with something like that. Log base 2 of x. Okay. Remembering from what we talked about just a little earlier, what would be the derivative of of this function. So what's the derivative in general of a logarithm? 1 over x. 1 over the natural log of the base, which is, in this case, is 2. So you might just see this as 1 over, a lot of times they put, no, they'll probably put the x first, natural log of 2. Okay. So that is all there is to taking the derivative of a log. Natural log, it becomes the natural log of e, which is just 1, so that's why you don't see it. And again, the only difficulty we're going to have with this is when there's a function in there, not just x, because we've got to use the chain rule, so we take the derivative of the inside part as well. Okay. So let's take this one. Let's go over here. G of x is equal to the natural log, and they'll put this with absolute values, and then in the book there's an example with natural or absolute values. Basically they're just showing that you can almost ignore the absolute values, but the absolute values, what do you know, what can we not put inside of a logarithm as input? So what's not part of it? Can't have negatives. You also can't have a 0, right? The natural log of 0 doesn't exist. If you put that in your calculator, it does. So that's why they have that's why they have the absolute values there. Okay, the input has to be positive. Okay. So when we go to take this derivative, what are we going to get? It's going to be 1 over the stuff inside, right? Because that's a logarithm. It's 1 over what's ever in there. And again, you could do this with u substitution, but I think it sometimes makes it more confusing. And then we got a chain rule says that gives us the derivative of the outside function of the logarithm, the natural log. Chain rule says we also have to take the derivative of the inside function. And what's the inside function? X squared plus 2. The derivative of the inside function is 2x. Good. So 2 comes down. Plus 2, that's a 0. So it's just 2x is our derivative. Notice, where is that 2x? It's up on top. So it doesn't go down with the other stuff. So that's the thing, is you'll see oftentimes when you see the derivative, it's just going to be whatever was inside the logarithms in the bottom. And again, nothing's really happened to it. And the top part is going to be the derivative of the bottom part. Okay. And that follows from the chain rule. And again, that's all there really is to it. There's a few in the book that, but they're not in the homework, that involve some multiplication and division, so that involves some properties of logs, where you have to add and subtract them. We don't get that complicated in the homework we've assigned you for WebAssign, and those kind won't be on the test, so don't worry about that. We're not going to get you into the algebra of logarithms. We're just going to give you, can you take a derivative? And again, the derivative is just going to, whatever's inside the logarithm goes into the bottom, all of it, nothing changed. The derivative of what's in there goes into the top, because we're multiplying by it. Simple enough. But again, it's also kind of weird, because it just is what it is. It's one of my brother's favorite rules. It is what it is. Just accept it. Okay. Let's do one more. It's a little more complicated. Let's do this one. Try to find the derivative of h of x. Again, I'll give you just a few minutes. See what you can do with it. Just take that inside stuff, put it underneath. Since it's not a natural log, we've also got a adjusting factor, remember? And then the derivative of the inside stuff all ends up in the top of the fraction. You just kind of learn that process, do it a few times. Maybe going into economics, okay, you might see some of it. If you get into deep economics theories, this is sometimes you're using more of the exponentials and stuff. Possibly with finance, but mostly it's economic theory where you might be using some of this. Marketing, you'll probably never have to worry about logarithms or exponentials. Business management, probably not. Again, just mostly finance or possibly, because economics is related to the finance part. So what do we got so far? What goes in the bottom? Good, just x squared plus x. I'm going to put a parentheses just around it because just to make sure it gets multiplied out. What else goes in the bottom? Excellent. That base needs an adjuster, and that is in the bottom because we saw that up here, right? So there's a natural log of 3 down here. And then what's going to go in the top? The derivative of this, which is 2x plus 1. So notice how we've gone so quickly. We got this power rule in the first day we looked at it, did 2 sections of that. We jumped into product rule, quotient rule, chain rule, and now we're already down here jumping into logarithms and exponentials. You know, they call this brief calculus, but it's not. It covers a lot of material in a short period of time, and we don't go too deeply. So that's the brief part. It's not deep, but it is very wide. Okay, because we're actually going to end up covering 2 semesters worth of calculus in this 1 semester class, but again, not as deep. Okay, still doesn't mean it's easy. Okay, and that's it. That's it. Right? The top part is the derivative of the inside. The bottom part is just because it was in a log, that's what happens is that goes down there, and this natural log of 3 comes from, it's a correcting factor for the base.
This is the chain rule?
It's the chain rule, yes, because it's the derivative of the outside of the function times the derivative of the inside of the function. So literally it is 1 over x squared plus x. That's the derivative of the outside function. The derivative of the inside function is 2x plus 1. Chain rule. And we just put it all together. So it looks like one thing. Does it feel doable? Okay. So I want to give you enough time to get working through it. The implicit ones, there's basically 2 types of problems, and I'm going to give you a few examples where I just kind of work through it, and I'll let you know this is where we get to sort of multivariate calculus. We're doing it actually 2 variables, not just 1 anymore. So let me see if I can explain this simply. take this one example. So the first thing is what we do is we'll start with an equation. Something like this, 4x squared plus 2y squared equals 12. So what we're looking here with an implicit derivative, we're looking for what is the derivative of y with respect to x, dy dx. So let's say that. So what I'm going to tell you is as we do this, and maybe I'll just do a few examples, notice we've got, over here we've got an x variable and we have a y variable. And we have constants as well. First of all, what would be the derivative of a constant? Someone said it. 0. Constants, derivative of constants are always 0. Exponentials are their own derivatives. So constants are 0. What would be the derivative of 4x squared? With respect to x, it would be 8x. Okay, so that part's the easy part. So that comes down. And over here, we can take the derivative of 12. We know that's going to be 0. So that's easy. We've done this stuff before. But now what do we do when we want to take the derivative of y?
The dy over dx.
Good. So we just take it, we treat it like it was an x. So if this was, what's our derivative rules say what would happen with this? This should become what? 4y. But notice this was a derivative of y, sort of with respect to x. So what we have to do, the first one was a derivative of x with respect to itself. So it's like dx dx, so we don't write anything. So all we have to do is we have to write this dy dx. Because it's signifying that we took the derivative of y, but we're really doing everything with respect to x. So that's the, and again in the book you try to read it and it's got all this funky notation and it's what's really going on, I don't know. But it's all it's doing is taking the derivative and saying, put this label on it and that makes it okay. So when we take the derivative of x, just do it. Don't worry about it. It's going to be fine. When you take the derivative of y, just do it, but make sure you put this dy dx thing as sort of a label to signify that we sort of cheated this way. We took the derivative, we're taking the derivative of y. And then in the end, what we want to do is we want to find what is dy dx equal to. So how do we figure out what dy dx is equal to? This is algebra time now, right? We've got to get it by itself. So what would you do first? Good. We should subtract 8x from both sides. And that's why it's nice to have 0 over here, because it makes the algebra really nice. 8x minus 8x, that's 0. So we end up with 4y times dy dx equals negative 8x. But dy dx still is not by itself, so what would be your next suggestion? To get dy dx by itself, say that again, divide by 4y. Exactly. So divide this side by 4y and divide this side by 4y. That and that cancel. So we are left with dy dx is equal to negative 8x minus 4y.
simplify that?
No. Well, sorry, yes. 8 and 4, yes, we can do that. Yeah, numbers can, yeah. But x and y, you can, yes. So then, yes, 8 divided by 4 is negative 2x over just y. Thank you. Sometimes WebAssign lets you get away with it. Sometimes they'll say, no, you didn't reduce it and knock it wrong. So yeah. Good catch. Seem okay? When you got x, just take his derivative, just like we've been doing. When you got y, take his derivative, just like we've been doing, but just put that dy dx thing. And then now we've got an equation. We've got to solve it for dy dx. Okay, that's about half of the problems. The other half, I don't know, there's 5 problems, or maybe there's 6. The other half, what they do is then they also have a point that they want us to evaluate this at. And then what we need to do is we need to get the equation of the line through that point. So that's a little more complicated, but it still involves this step of finding the implicit derivative, which is take the derivative of x just as it is, take the derivative of y as it is, but put that dy dx thing in, and you'll be fine. Okay. So does it seem okay? And again, we didn't use all the notation that they did because I was getting a headache just trying to go through it. And I'm a math major, and it's like, I know this is just simple stuff. I mean, the process, I knew it was, but if you try to follow with the symbols they use, d dx and dy dx, it's intimidating, even to a math guy. Okay. Let's see, let's try to keep it kind of simple, and then let's, maybe before we move into that one, let's do one of these. It's got a little, oops, I forgot to plug this thing in again. I don't think we need the calculator. I'll make it through the night. Okay. So here's a complication that occurs, but we can handle it. We won't make it too complicated. Gee, that's really obnoxious. Let's make it a little challenging without... Here we go. This one will... So this is the equation we're going to look at. 2x squared plus xy equals 3y squared. So notice there's no function notation here or anything. These are actually not functions. What these would graph as is sort of circles or ellipses or something. So that's why, but sometimes they get used. So let's first go through and talk about how we would take this derivative. Does anyone see a place that might be a little challenging? xy. And we'll deal with it. Okay, so let's deal with the easy stuff. How about 2x squared? What would be the derivative of 2x squared? 4x. That's it. That's all there is to it. Good. So we just take its derivative, 4x. Subtract 1 from the exponent. There we are. How about 3y squared? 6y times dy dx. dy dx. And again, y is just sort of like a label that goes, whenever we take the derivative of y, we have to sort of say, hey, I took the derivative of y with respect to x. Okay. The other one is the derivative of x with respect to x, so that's dx over dx, which is just 1. Okay, so you could write that if you wanted to, but that's what's really going on. You're taking the derivative of x with respect to x. This time we're taking the derivative of y with respect to x, so we have to write that. What's going to happen with x times y? It's x times y, so when we take a derivative of things that are multiplied, what do we have to apply? product rule. Right? So we don't do the division, so it's just the product rule. Remember the product rule is we look at them as separate things. We take the derivative of the first, just copy the second one. Okay, so, oops, wrong place. So this is going to split into two different things, right? We first take the derivative of x, which is 1 times y. So it's going to be 1 y. So this 1 is the derivative of x. Okay. The second part, using the product rule, right, is to just copy down the first one, copy down the x, and then take the derivative of y. What's the derivative of y? It's 1. Is that all it is? Whenever we take the derivative of y, what do we have to write? dy dx. Okay, that's the main thing. Whenever we take this derivative, we write it down. And then we have the equal sign here. Okay, so that complicated thing in the middle, notice it's really just y plus x dy dx. But I've got this 1 in here just to remind us we're using a product rule. We're taking the derivative of the first one times the second one, nothing done, plus the first one with nothing done times the derivative of the second one. So whenever we've got a product, we always have to use this product rule thing. And we're still not done. Now we need to solve for dy dx. Okay, so let me simplify the writing here. This is 4x plus y plus x dy dx equals 6y dy dx. And we need to solve for dy dx. So what do you suggest? Got the dy dx things on both sides of the equal sign. We're going to solve for it. What should we do? We will eventually, but if we divide by 6y at this step, we would divide here. We'd have to divide all of these by 6y, and we would still have the dy dx's on opposite sides. We want to get over so we're getting 1 dy dx. Yeah, so let's bring them together. So since this side only has one thing, if you subtract, let's go with red. If we can subtract x dy dx from both sides, see, the algebra is just kind of not really nice. Okay, what happens here? Plus x minus x, 0, it cancels. So then we're left with 4x plus y. That's all that's there. This side, we've got 6y dy dx minus x dy dx. You're right, we're going to divide by the thing in front of the dy dx, but what do we need to do? How can we get dy dx to just be one thing instead of two things? What if we had try to make it so it's what if I had 6x squared plus 3x? Can I rewrite this algebraically? Factoring, right? There's a 3x in both of these, so I can take a 3x out. and I'd be left with 2x plus 1. So if you multiply back by 3x, you got what you started. This is what we're going to need to do if we factor. Down here, what is the common factor? Because remember, these are being multiplied, right? What's the common factor? dy over dx. So what we do is factor out dy dx, factor it out. What's left behind is 6y minus x. I remember the day this kind of clicked for me. It wasn't the first day I saw it. It wasn't the 100th day I saw it. It was after many years of struggling with it. One day I finally, it just clicked. Oh, we're just factoring. But that's what you need to do with these. I think there's one problem like that. What's that? Yeah. So this is the trick, okay? You're going to see it to get them on the same side, factor it out, okay? And what's left? What's there left to do now? Okay, so now how do we get the dy dx by itself? Alina? Divide by that whole, yes. So this time, it's just kind of, it's a little more complicated than what we started with, but we now divide this side, 6y minus x, that's going to cancel. And so we have to divide this side, oops, 6y. And actually, you thought this was an 8-week class, but actually the way I'm doing this, we're going to be done in 6 weeks, so that you've got the last 2 weeks to study, and I think it'll work. We'll see. So far, the results of those who've taken the exam, I think you've done a pretty good job, especially by the time you do some test corrections. You should all, most of you are going to be in just fine shape. And remember, we'll have another chance and all that kind of stuff. So what's our final answer? Let's see. These guys cancel. dy dx is equal to this fraction. So maybe we write that up here somewhere. So dy dx is equal to 4x plus y over 6y minus x. No. Yeah. And that's the nice thing, is most of these they will not, in fact they'll tell you, don't simplify algebraically once you get to something like this. But this is about as complicated as it gets. It's because of that product rule and plus having 2 y terms. We had 3 y terms, we'd get 3 terms that have a dy dx, and we've got to factor more things out. But if you just remember that, that's a key part. dy dx, if you have more than one, just get them together, factor them out, and divide by all the stuff that's in there. And that's valuable. Okay. You ready for the last step?
This is 11.6.
What? It's 11.6. Thank you. I think I did. But I did call it implicit differentiation. But let's go back a page. Right. Thank you. So now I'll come back here so that in the notes it'll say 11.6. And only those who watch the video will know that it ever said 10.6. We'll fix that. Okay. So we'll go forward. Oops, went the wrong way. There we are. And then I'll ask for a new page. And I'll go over the last one, which is really this. But where are my notes? Okay, here it is. Not that one, not that one. Okay. Oh, where's... Okay. Make it a little bit And then what we'll do is we'll take a look at the homework. If they look doable, we'll just let you do them. But if there's one that looks a little challenging, we'll go through it together. And you guys get to decide, not me. So, okay, so I'm going to take this one, 3x squared minus y squared equals 11. And in this one, they're going to give us a point, -2, 1. The questions are going to be find dy dx, just like we've been doing, so that's nothing new. But the other thing is find equation of tangent line. At the given point. Okay, so that'll take us back a little bit. So a little bit of calculus, that tangent line thing is going to bring us back some algebra, but we'll be okay.
Is that a point or interval?
It's a point. Good point, yeah. So this is a point. Because it can be ambiguous, right? So let's say the equation of the tangent line at the indicated point on the graph. Okay, so the steps are first to find the implicit derivative. So first step, derivative. And so we come to 3x squared, and what's the derivative going to be? Excellent, 6, 2 times 3. Subtract 1, it's just x. How about minus y squared? Very good. Every time we take the derivative of y, we just put this dy dx, and it's all good. We don't know why, but it just works, so we do it. And the derivative of 11, 0. So that's the other thing. Derivatives of constants are always 0. We solve this for dy dx, so this is the algebra part. We subtract and then divide by the thing in front. Okay, so I'm going to subtract 6x from both sides. That's gone. We got minus 2y dy dx equals negative 6x. Now what do we do? Divide by this negative 2y because we don't want that in front. And so we have simplified this thing down. And we have dy dx, because this stuff cancels, right? Equals this fraction here. Can we go ahead and simplify? 6 divided by 2 is 3. Negative and negative make it positive, so it should be just 3x over y. Now, what is dy dx? What is a derivative? It's the slope of the tangent line. Okay, so that's what we found. Dy dx is a formula for the slope. So that's just have to remember what we've got is a slope. It's a rate of change. So at this particular point, what we could do is we could plug in the x value for x, the y value for y, and that will give us the actual slope at that point. Okay, so let's do that. So I don't know about special notation, but just so this will be one answer in the WebAssign homework, and there'll be a place to fill that in. The next step is to take this, plug in the x coordinate for the x, the y coordinate for the y. So we end up with 3 times negative 2 over 1. And so what's our slope? Negative 6. at that particular point. Okay, so far the equation of our line, remembering from algebra, y equals mx plus b, y equals negative 6x plus some y-intercept, right? How do we find out what that y-intercept is? Plug in x and y. Because then we'll have an equation that has one unknown, so we use the same x and the same y because it's going through that point. This line goes through that point. And so, again, for a second time, we plug in 1 for y, we plug in negative 2 for x, and then we solve for b, we'll have our y-intercept, and that way we'll have our equation. So this is all algebra. It's not, at this point, it's not calculus. So what do we end up with? We end up with 1, negative 6 times negative 2, positive 12 plus b. So to get b by itself, subtract the 12, and we end up with b equals a lovely negative 11. And so our answer is going to be y equals negative 6x minus 11. And that will go in the second slot in the WebAssign. And again, I think that there's 5 or 6 problems at the most. I think about half of them just have you find dy dx. The other half have you find dy dx and then find this equation of the tangent line. So it involves plugging it in to get the slope, and then plugging that same point in again to find the y-intercept, and to get that answer. How's that? So far so good. Okay. Questions? And on some of these, the algebra gets a little tricky, and on the previous assignments as well. If you've got, once you've done it the third time and your answer looks pretty close, like we were working it last week, and either they factored out a negative or we factored out a negative, so that algebraically we had the same answer, but they looked a little, and it was counting it wrong. Just maybe send me an email. I don't think I ever got the one through WebAssign, but get in touch with me and just let me know, hey, question this from this assignment is pretty much right, because you can see the answer, you can see yours, and I can add those points in, rather than you going through work a whole nother one, because sometimes it's just there's a few in there where the algebra gets a little obnoxious. Okay, so we'll look at this. And let's take a quick look at 11.6, because that's a shorter one. Oh, there's only 5. Yeah, so there's one fairly straightforward, just an x and y, find dy dx. There's one that you're going to need to use the product rule here. And there's 2 y's, so you're going to end up with 2 y dy dx's, so you're going to need that trick of factoring. Okay, so that's why I did show it to you. This one also, you've got 2 y's in here, so you're going to have 2 dy's dx, so another one you're going to need to do the factoring on. This one, a lot of words, but basically the same thing. Find dy dx, and then just do what we just did. Additionally, plug in the point to find the equation of the tangent line. And again, a little bit more reading, but it just basically says find dy dx. Once you have that, plug in the point, and then find the equation of the tangent line. So a couple challenges. In fact, actually, well, it's almost like the one we worked, doesn't it? I don't know what yours will look like, but sometimes I think they only change the red stuff, so the point will change, but the derivative, if you took notes on it, I think we already did that one. It's pretty close to the one we worked on. So that's the one we had to factor out at the end. So some of these, we did the heavy lifting already. Okay, and then let's just take a quick look at 11.5, just to see if there's anything that you might want to. Say 15 problems, so there's more of them. Again, a natural log base 7. Again, these are fairly straightforward. Remember the absolute values, don't worry too much about that. Those look pretty straightforward. E to the x plus 2, e to the 7 minus x, so they just reversed it. I think these are not. Now this one, what are you going to need to use on this one? Which one of the rules? I mean, the chain rule comes every time we do the log, but there's nothing in there. But this is 8x times natural log of x, product rule. So derivative of the first part times the second one unchanged, derivative of the second with the first unchanged. And you'll see the second one, you'll get 8x over x. You'll see some of it cancels out. So just to get you ready there. This one, again, product rule here. So just, yeah. And I think everything else is pretty straightforward and doable. Okay? So if you got the time, make sure you get that test done. Test corrections. Yes, sir.
I have a question on the way you find the derivative of e of x. So the derivative of e of x is e of x.
Yes.
Right? But the derivative of like e of 2x minus 1 is not e of 2x minus 1. So why?
Actually, it is. E of 2x minus 1. So if we take its derivative, it is e to the 2x minus 1. But because of the chain rule, we've got something inside the exponent. It also means we have to take, so let me back up. Let me do it this way. E to the x, the derivative of e to the x is really itself times the derivative of x. What's the derivative of x?
1.
1. So it ends up being,
Oh, okay. Well, that makes a lot more sense.
okay, that's, yeah. So we always take that derivative, but right, when it's x, it just becomes 1, and so it's like we don't think we did it. I think that's what finally made sense to me too.
Okay, yeah, because that really threw me off when you were doing the,
Okay. Yeah, it seemed like there was a different rule if it was more complicated, but it's really the same rule. It's just when it's just e to the x, the derivative of the exponent is just 1.
It's just okay, yeah, it's times the derivative of the exponent.
Yes, yes, think of it that way, and you'll always get it. Very good. All right, so we're going to cut the live streamers off. Hopefully it was live streaming all the way along. And then we're here to help you out.